In the previous chapter, we clustered the Costa minimal mesh into 2 sets of mesh strips, with 48 strips in each. In this chapter, we modify these strips by giving them some inset along the longer edges. These insets will accommodate any possible clash between the strips arising due to material thickness. Let's understand the workflow before we build the definition. For the warp strips, we would like the insets like this. And for the weft strips, we would like the strips to be like this. Since there is no direct way of doing this, we will have to start by extracting the internal edges from each strip, and the shorter naked edge. Let's assume this strip, and these are the lines extracted from the strip. We have to run 3 steps to get to the inset geometry. Shorten the length of each line by 0.25 mm from start and end. Align the direction of each line belonging to one strip, that is, the start and end points must be aligned. The lines must be listed in a sequential order to enable lofting between the curves. Once this is done, we can loft the curves, and get the B-reps version of warp and weft strips. As always, you may open the Grasshopper file from the resource folder to follow along. Let's begin building this definition by analyzing the geometry. In both warp and weft mesh, we see 2 types of strips. One is a linear type that spans between naked edges, and the second is the loop kind that forms a closed loop. Both require slightly different definitions to rationalize. So, right at the beginning of step 2, we will split the list of mesh strips into linear strips and loop strips. Let's start with the warp strips. Extract the naked edges of the strips. This gives us a data tree with 48 branches. 1 branch for each strip, and each branch has multiple naked edges. Join these curves, and we again get a data tree of 48 branches with either 1 or 2 polyline curves. This happens because loop strips have 2 polylines representing the naked edge, whereas the linear strips are represented by 1. Extract the list length from the join curves component, and use a mathematical operator to check if the list length equals 1. This will give us a Boolean list that can dispatch the strips into 2 lists. List A is the list of linear strips, and list B is the list of loop strips. Separate them into different mesh container components. If we pull up a panel and look at the list, some branches are empty due to the dispatch function. So before moving to the next step, we need to clean the tree, and remove all empty branches. Once we have isolated two types of strips, we can now build the definition for each type. Let's begin with the linear type, which has 32 strips. The first step is to isolate all interior edges, by using the Mesh Edges component. Then we have to identify the start and end edge from the list of naked edges. To do this, we first try to identify the naked vertices that do not coincide with the endpoints of interior edges. Collect all endpoints of interior edges into one point container. And all the naked vertices into another. Use the member index component to identify the indices of naked vertices that coincide with endpoints of interior edges. Connect naked vertices to set input and endpoints into member input. This gives us the list of indices. Simplify the index output, and let's understand the data structure. The data tree is divided into several branches. The path of these branches has two levels of hierarchy. The first number relates to the strip, and the second number relates to the endpoints that the item represents. We must collapse the second hierarchy such that every index belonging to a single linear strip is listed within a single branch. Use the trim tree to trim the last branch. Set the depth input to 1, which means that we want to trim only the last branch. The output from trim tree is a data tree with only 32 branches. Use this data tree of indices to cull items from the list of naked points. This leaves us with 4 points per strip, represented by branches in the data tree. These 4 points are the endpoints of the two edge curves we want to isolate. We can use the point groups component to group the points based on proximity. This is a critical step because the distance parameter is geometry specific. We have to set the parameter to a value that will group these 2 points in one branch, and the other two in a separate branch. Approximate length of these edge lines appears to be less than 15 mm. So let's set the distance parameter to 15. Check the group's output for resulting data tree. We need to ensure that for 32 branches, each branch of the resulting data tree should be subdivided into 2 branches. That means we must have 64 branches. Connect the group's output to Param Viewer. It reads that the data tree has 128 branches. That means that the distance threshold is lower and needs to be increased slightly. Keep increasing the value till we get 64 branches in Param Viewer. At number 20, the Param Viewer reads 64's branches. Use a list item to extract the 2 points from each branch, and draw a line to connect them. Use Trim Tree to combine the line belonging to the same strip. Merge these two lines with the interior lines. Ensure that the input of the merge component is simplified. Sometimes, the path hierarchy of two data trees do not match, and the data fails to merge. Simplifying the input data in the merge component helps resolve this issue. Now that we have the lines for each strip, we must align the lines in the same direction. For this, we need a guide curve which will be the polyline formed by joining the remaining naked lines. To extract the remaining naked lines, take the complete list of naked edges, and find their midpoint. Also, find the midpoint of the two naked edges isolated in the previous step. Use member index to identify the index from the complete list of naked edges, which coincides with the two we had identified. Simplify the output. Trim the tree. And cull those two indices from the complete list of naked edges. Now use the Join Curves component to join the remaining naked edges. This gives us two polylines for each strip. Use List item to take either one of these polylines as guide curves. At this stage, we should have a list of lines for lofting, which have 32 branches and 17 lines in each branch. And we must have a list of guide curves with 32 branches, and one polyline in each branch. To align the direction of loft curves, we will find the start point of each curve, and check the distance from their respective guide curves. If the distance is 0, then the loft curve's starting point is towards the guide curve. If the distance is non-zero, then the loft curve's start point is away from the guide curve, and must be flipped. Bring curve closest point component into the canvas. Connect the guide curves to the curve input. Use the endpoints component to extract the start point of loft curves, and connect to the point input. Use a mathematical operator to test whether the distance's values are less than 0.01. This gives us a Boolean list that can be used to dispatch the loft lines into two lists. Flip the curves in list B using the flip curve component, and merge them with list A curves. This ensures that the directions of all loft curves are aligned. The next step is to arrange the loft curves in order. Currently, the loft's curves of any strip are listed in random order. You may use point on curve, and then point list to view the order. So set these in order. We again use the polyline as guide curve to sort the loft curves. Extract the start point on each loft curve. Then sort the list of points using sort along curve component. This gives a list of indices that can be used with list item to sort the loft curves. The resulting lines are now listed in a directional order. Next step is shortening these lines by 0.25 mm from both ends. Use the extend curve component for this. Connect the loft curves into the curve input. Set the start and end value to -0.25. This gives us a list of shortened lines. The last step is to group these lines in pairs of 2 for lofting. For example, we have 17 lines for each strip. Use cull index to remove index 0 of each branch. Then use the shortest list component, with the culled list as list A, and other curve list as list B. Graft, simplify, and merge list A and list B. And we get a data tree with multiple branches, and each branch has 2 lines each. Loft these curves, and we get a list of surfaces representing the inset faces of our original mesh strips. Trim the tree so that all faces belonging to one strip are within the same branch. Now that we have the shortened surfaces for the linear strips, we will learn how to extract the shortened surfaces for the loop strips in the next chapter.